I'm Andreas Hamberger, and this is the Hamberger Report, where I cover AI governance, enterprise architecture, and the technology decisions that actually matter to the people who have to make them. If you find this useful, subscribe and hit the like button. It helps more professionals find the channel. Now let's get into it. %45%. That is the proportion of AI-generated code that introduces security vulnerabilities, according to Veracode's 2025 GenAI Code Security Report. Across Java, Python, C# and JavaScript, the models chose the insecure implementation nearly half the time. Java was worst, a 70% failure rate. When the models generated code to defend against cross-site scripting, 86% of samples failed. I'm Andreas Hamberger. This is the Hamberger Report, where I cover enterprise architecture in the age of AI agents. This is Zero Trust Thursday, and this episode is Chapter 2 of Zero Trust Architecture for the Agentic Enterprise. To secure AI systems, you do not need a PhD in machine learning, but you do need to understand how large language models work, because that understanding tells you where the attack surface lives and why your existing controls are failing to close it. Long a user sends a prompt to a language model, the system does not understand the request. It executes a pipeline. The prompt first passes through a tokenizer, which breaks text into fragments and maps each to a numerical identifier. Adversarial inputs that look benign to a human reviewer can exploit tokenization quirks to change meaning at the numerical level. Those tokens then pass through an embedding layer, converting each identifier into a high-dimensional vector representing meaning. The critical security insight, embedding inversion attacks can reconstruct original text from those vectors. If your RAG system stores embeddings of sensitive documents, those embeddings are not anonymized data. They are recoverable data. The attention layers and generation stage that follow carry their own attack surfaces. Every stage in the pipeline is a potential point of security failure, and that is before anyone outside your organization gets involved. Every language model operates within a context window, a fixed size buffer that holds everything the model can see at once. Your system prompt, the user's input, retrieve documents, tool outputs, conversation history, all of it in the same space at the same time. The context window has no access controls. There is no privilege separation, no memory segmentation, no hardware-enforced boundary between your trusted security instructions and untrusted user input. For security architects accustomed to network segmentation, this is the equivalent of running your firewall rules and your application logic through the same processing pipeline as user input, with no isolation whatsoever. This is why indirect prompt injection is so effective. An attacker does not need to interact with your LLM directly. They embed instructions in a document that gets retrieved into context, in an email, an AI assistant processes, or in a web page, an AI agent visits. The model treats those injected instructions with the same weight as your system prompt, because at the token level, they are indistinguishable. OWASP places prompt injection at number 1 in the top 10 for LLM applications. For precisely this reason, it is not simply the most common attack, it is architecturally fundamental. In New Zealand, the 2025 GCDO cross-agency survey counted 272 AI use cases across 70 government agencies, with 55 now operational. Many of these use AI-enhanced search, feeding retrieved documents into a shared context window. Those documents carry NZISM classification levels and Privacy Act obligations. Long context window does not respect your classification levels. That is not a criticism of the technology. It is a design fact that must drive your architecture decisions. Security architects must distinguish 3 phases of an LLM's lifecycle, because each carries a fundamentally different threat model. Training is where the model learns from massive datasets. The security risk is foundational. If training data is poisoned, the model's behavior is compromised at the deepest level. You cannot patch a poisoned model the way you patch a vulnerable application. The contamination is distributed across billions of parameters, with no clear mapping between specific training data and specific outputs. Fine-tuning adapts a pre-trained model for a specific task using a smaller curated dataset. This is where many organizations customize models for their environment. The threat shifts. A compromised fine-tuning dataset can introduce targeted behaviors that do not manifest during standard testing. For organizations fine-tuning models with government or personal data, the Privacy Act's Information Privacy Principle 5 applies directly. Personal information embedded in model weights cannot be deleted, searched, or audited the way a database record can. Inference is what happens every time someone sends a prompt. IBM's 2025 Cost of a Data Breach report found 97% of organizations experiencing AI-related security incidents lacked proper AI access controls. The reason controls fail across all three phases comes down to one fact: the model is not retrieving information. It is predicting the next most likely token in a sequence. That probabilistic nature breaks fundamental assumptions about testing, validation, and audit. The same prompt can produce different outputs on successive runs. Hallucination rates in unverified deployments run between 8 and 15%. In a security context, a hallucinated configuration recommendation is not merely unhelpful. It is actively dangerous. Treat every LLM output as untrusted input. That principle governs every architectural decision in this series. The attack surface exists at every layer. Input attacks target the prompt and context window. Direct prompt injection, indirect injection through retrieved documents, jailbreaking. In late 2025, the GreyNoise threat intelligence team documented over 80,000 enumeration requests against LLM endpoints, systematically probing model infrastructure with the hallmarks of professional reconnaissance. Threat actors are building target lists. Model attacks target the weights and training process. Output attacks exploit generated content, including insecure handling, where LLM outputs trigger cross-site scripting or SQL injection in downstream systems. Integration attacks target RAG pipelines, tool connections, and the trust relationships between agents. A 2025 disclosure documented a second-order prompt injection, where a low-privilege agent caused a high-privilege agent to export entire case files to an external URL, bypassing access controls entirely. The attack exploited not a code bug, but a trust relationship. From this, 5 principles must govern every architecture decision. 1. All context is untrusted. Treat every input as potentially adversarial. 2. Outputs require verification. Never allow LLM output to trigger privileged actions without external validation. 3. Deployment architecture is security architecture. The choice between a commercial API, a self-hosted model, or a RAG-augmented system is a security decision with direct regulatory implications. 4. Traditional controls are necessary but not sufficient. You need controls that operate at the logic layer, not just the network layer. 5. The threat model is active and evolving. 80,000 enumeration requests. Professional reconnaissance. This is not a future risk. Chapter 3 next Thursday. Zero Trust Fundamentals for the AI practitioners who build these systems. If you are an architect or CIO figuring out what Agentic AI means for your practice, subscribe to the Hamberger Report, new videos every day. And if you want structured TOGAF training adapted for the Agentic age, the link to my practitioner course is in the description. That is the Hamberger Report for today. If this was useful, subscribe and hit the like button. It helps more professionals find the channel. You will find links to everything we covered in the description below. I am Andreas Hamberger, and I will see you tomorrow.